The global digital economy relies on a single geological formation in Spruce Pine, North Carolina. This site produces over 85% of the world's high-purity quartz. This material is essential for manufacturing the crucibles used to grow monocrystalline silicon ingots. Global demand for semiconductor-grade high-purity quartz has risen from 22,000 metric tons in 2018 to an estimated 36,500 metric tons in 2024. This growth is driven by massive expansions in 300mm wafer fabrication. As shown on the chart, global demand surpassed Spruce Pine's standalone capacity in 2021. This structural deficit is projected to reach 5,000 metric tons by 2026. The industry now relies on dwindling stockpiles, synthetic alternatives, or lower-grade blending to bridge the gap. The bottleneck is not a matter of mining volume, but of atomic-level purity. Advanced node silicon manufacturing requires quartz with total impurities below 15 parts per billion. Spruce pine quartz exhibits a total impurity profile of just 10.4 parts per billion. Alternative deposits in Russia and Norway exceed this critical 15 parts per billion threshold. They contain elevated levels of aluminum and iron. At temperatures exceeding 1400 degrees Celsius, these impurities migrate into the silicon ingot, ruining its crystalline structure. Refining lower-grade quartz from deposits like Donghai, China, is not a viable short-term solution. The chemical processing required increases costs by 300 to 400%. It also generates substantial hazardous waste, limiting rapid scaling. This supply constraint has triggered extreme procurement latency. Average lead times for high-purity quartz crucibles have escalated from 12 weeks in 2018 to 52 weeks in 2024. The spot market price index has nearly tripled over the same period. Yet, this bottleneck exhibits extreme economic asymmetry. Quartz crucibles represent less than 2% of total wafer manufacturing costs. Because a crucible shortage halts 100% of silicon production, buyers are highly price inelastic. This vulnerability mirrors the early 20th century global dependence on Chilean natural nitrates before the Haber-Bosch process. Today, the physical layer of advanced computing remains hostage to a single geographic point of failure. The modernization of the global electrical grid is colliding with a severe chemical bottleneck. Regulatory mandates are forcing the rapid phase-out of sulfur hexafluoride. This gas is the industry standard for high-voltage insulation, but possesses 23,500 times the warming potential of carbon dioxide. As shown on the chart, this regulatory shift has caused procurement lead times to balloon. By late 2024, average lead times for sulfur hexafluoride-free switchgear reached 60 months. This represents a 233% increase in procurement latency since 2018. Even traditional equipment now faces a 42-month wait. The transition is not a simple chemical substitution. It requires entirely new physical architectures. This bottleneck is systemic across the global manufacturing oligopoly. The three dominant grid infrastructure producers face unprecedented backlogs. Combined orders for Siemens Energy, Hitachi Energy, and GE Vernova reached $75.5 billion in 2024. This represents a 178% increase from 2019 levels. Hitachi Energy experienced the largest absolute growth, with its backlog rising to $31.2 billion. This surge is driven by high-voltage direct current projects and alternative switchgear mandates. GE Vernova's grid segment backlog grew at a 24% compound annual rate. The physical capacity to build transmission equipment cannot keep pace with capital allocation. The bottleneck is rooted in the physical limits of factory retooling. Transitioning a single production line for regional transmission switchgear requires $16 million and 18 months of physical reconstruction. At ultra-high voltages, these requirements escalate to $35 million and 30 months. Furthermore, the transition introduces new chemical dependencies. While lower voltage classes use clean air, transmission-grade systems require proprietary fluoronitrile gas mixtures. This concentrates supply chain risk in specialized chemical processing nodes. This transition resembles the chlorofluorocarbon phase-out under the Montreal Protocol of 1987. Once again, regulatory mandates are forcing a capital-intensive redesign of heavy industrial infrastructure. Western aerospace sector faces a severe upstream vulnerability in its titanium supply chain. In late 2020, the United States lost its entire domestic titanium sponge production capacity. The idling of the Henderson, Nevada plant left the nation 100% reliant on foreign imports for this critical defense material. Meanwhile, China has aggressively expanded its processing infrastructure. Chinese domestic sponge capacity more than doubled between 2018 and 2023, now controlling over 58% of global output. This leaves Japan as the sole major Western-aligned supplier of high-purity sponge. This concentration creates an acute single point of failure. Prior to 2022, Western aircraft manufacturers relied on Russia's VSMPO Avisma for over one-third of their aerospace-grade titanium. Decoupling from Russian supply has forced a rapid, highly fragile reallocation of capital to Japanese and Kazakh refiners. Securing raw titanium sponge only shifts the bottleneck downstream to physical deformation. Large structural aerospace components, such as landing gear and wing spars, require ultra-heavy hydraulic forging presses. The global inventory of these machines is dangerously small and highly consolidated. The United States relies on just 3 operational presses capable of exerting over 45,000 metric tons of force. 2 of these units were commissioned in 1955 under a post-World War II military program. These 70-year-old assets represent a fragile foundation for modern defense manufacturing. In contrast, China operates the world's most powerful press in Dayang, capable of 80,000 metric tons of force. Commissioned in 2013, this modern infrastructure allows China to forge massive, single-piece titanium bulkheads. Replacing or expanding Western forging capacity is constrained by extreme capital and time barriers. A single new heavy press requires over $150 million and up to 6 years to engineer, install, and certify. This physical reality prevents any rapid response to sudden supply disruptions. The physical layer of the global internet is highly concentrated. Over 99% of intercontinental data traffic relies on approximately 500 active subsea fiber optic cables. This entire network is installed and maintained by a tiny, stagnant fleet of fewer than 60 specialized vessels. As shown on the chart, this critical maritime asset class is aging rapidly. In 2015, only 19.3% of the fleet was over 20 years old. By 2024, that share rose to 44.8%, representing 26 out of 58 active hulls. Replacing these vessels is constrained by high capital barriers and limited shipyard capacity. A single modern cable-laying vessel costs over $120 million. Specialized shipyard backlogs have pushed delivery lead times to between 36 and 48 months. This capacity deficit has pushed the remaining fleet to its operational limits. Global fleet utilization reached 94.8% in 2024. This leaves virtually zero redundancy for emergency repairs or weather disruptions. Consequently, repair latency in the Pacific theater has surged by over 350% since 2018. The average wait time to repair a severed subsea cable has risen from 5.2 days to 23.5 days. This operational strain is worsened by geopolitical friction. In contested zones like the South China Sea, permit delays frequently hold repair vessels in port for up to 45 days. The physical layer of the internet is increasingly vulnerable to prolonged, systemic outages. The medium-term outlook indicates a severe structural divergence. Driven by hyperscale cloud expansion and artificial intelligence clusters, annual subsea cable installation demand will reach 210,000 kilometers by 2030. This is nearly double 2024 levels. Yet, the active global fleet is projected to contract to just 51 vessels by 2030. This contraction is driven by the retirement of aging hulls built during the late 1990s telecom boom. To meet demand, average installation capacity per vessel would need to increase by over 110%. This is an engineering impossibility. This bottleneck mirrors the late Victorian era, when Great Britain's control of the cable-laying fleet, led by the steamship Great Eastern, dictated global telecommunications. Today, the constraint is not national monopoly, but a systemic deficit of heavy industrial maritime assets. Global aluminum supply chain is increasingly dependent on a single West African nation. Guinea now controls over 70% of China's bauxite imports, up from 46.1% in 2018. This geographic concentration exposes the global smelting sector to severe systemic risk. This dependency accelerated after June 2023, when Indonesia implemented a total ban on raw ore exports. As shown on the chart, Indonesian supply to China collapsed from 19 million metric tons to just 2.1 million metric tons in a single year. Chinese smelters shifted their procurement entirely to Guinea to maintain production. This shift drove a massive expansion in Guinean export volumes, which reached 99.1 million metric tons in 2023. The entire Chinese aluminum industry, critical for automotive and aerospace manufacturing, now relies on this single bilateral corridor. This massive trade volume is constrained by a severe domestic infrastructure deficit. Guinea lacks deepwater port berths capable of hosting Cape-size bulk carriers. Consequently, exporters must utilize a highly inefficient, multi-stage transshipment process. As detailed in the cost breakdown, domestic logistics total $17.20 per metric ton. This exceeds the actual cost of mining and processing the raw ore. Shallow draft barge transshipment alone adds $5.50 per metric ton. This cost acts as a permanent structural tariff on Guinean bauxite. Because the Rio Nunes and Rio Conera rivers have draft limits of under 5.2 meters, direct loading of large ocean vessels is physically impossible. The entire supply chain is held hostage by river geography. This transshipment model introduces extreme vulnerability to seasonal weather. During the summer monsoon from June to September, heavy rainfall and high seas disrupt operations. Open water transfers are suspended on average 18 days per month when wave heights exceed 2 meters. As shown on the chart, monthly export volumes collapse by 46.9% during the wet season. Output drops from a peak of 9.8 million metric tons in March to just 5.2 million metric tons in August. This seasonal bottleneck triggers massive financial penalties. Delayed Cape-size vessels stranded offshore accumulate demurrage fees of $22,000 to $35,000 per day. This operational fragility mirrors the 19th century grain trade bottlenecks on the Danube River. Once again, global commodity markets are constrained by localized physical bottlenecks and a deficit of heavy industrial infrastructure. The global transition to green hydrogen faces a hard geological limit. Proton exchange membrane electrolyzers require iridium, one of the rarest elements in the Earth's crust. Global annual supply is stagnant, averaging just 7.5 metric tons. As shown on the chart, this fixed supply is incompatible with decarbonization targets. Under the International Energy Agency's net zero pathway, iridium demand from electrolyzers will reach 21 metric tons by 2035. This single application would require nearly 3 times the current global production. The structural deficit manifests in 2029. At that point, electrolyzer manufacturing alone will consume over 112% of global supply. This physical bottleneck threatens to halt the scaling of the hydrogen economy. To bypass this bottleneck, manufacturers must reduce the amount of iridium used per kilowatt. At current commercial loading levels, allocating half of the global iridium supply limits annual manufacturing to just 8.75 gigawatts. Scaling to 70 gigawatts annually requires a 90% reduction in catalyst loading, down to 0.05 grams per kilowatt. However, this thrifting strategy faces severe physical constraints. Reducing iridium below this threshold accelerates membrane degradation at the anode. This shortens the operational lifespan of the electrolyzer stack below the 80,000-hour commercial benchmark. The industry faces a direct trade-off between material scarcity and equipment durability. The physical supply chain is highly concentrated. South Africa controls 83% of global iridium extraction. This concentrates the entire upstream supply chain within a single, fragile infrastructure network. South Africa's state utility, Eskom, suffers from chronic grid instability. Stage 6 power curtailments directly disrupt energy-intensive smelting and refining operations. This grid vulnerability makes global green hydrogen targets hostage to local power outages. Russia is the only significant alternative supplier, controlling 11% of global iridium. This concentration mirrors the 1970s catalytic converter crisis, which forced automakers to secure direct physical supply lines. Today, Western manufacturers face a choice between South African grid failure and Russian geopolitical risk. The global battery supply chain is undergoing a structural realignment. High-pressure acid leach facilities in Indonesia are rapidly expanding. This expansion has unlocked massive deposits of low-grade nickel-cobalt laterite ores. As shown on the chart, Indonesian mixed hydroxide precipitate, or MHP, is scaling rapidly. Output of contained cobalt in MHP is projected to rise from 1.5 kilotons in 2020 to 105 kilotons by 2028. This represents a compound annual growth rate of nearly 70%. The Democratic Republic of Congo remains the largest absolute source of cobalt intermediates. However, the rapid rise of MHP has altered the global feedstock mix. The primary intermediate is shifting from crude cobalt hydroxide to MHP, which contains both nickel and cobalt. Geographic diversification of raw extraction has not broken the geopolitical bottleneck. The chemical processing of MHP into battery-grade chemicals remains concentrated in China. As the chart illustrates, China's share of global cobalt refining capacity has expanded from 68% in 2018 to an estimated 79% in 2024. It is projected to reach 81% by 2026. Meanwhile, Western refining capacity has stagnated or declined. Finland's share fell to 7%, and Canada's dropped to 2.5%. This means that even as Western automakers source Indonesian MHP to bypass the Congo, the material must still pass through Chinese-controlled refining assets. The processing bottleneck has actually tightened. The transition to Indonesian HPAL technology introduces severe economic and environmental trade-offs. As detailed in the table, these projects require $65 million per kiloton of annual capacity. This is nearly 2.6 times the capital required for traditional Congolese routes. Furthermore, the carbon footprint of Indonesian MHP is more than double that of the Congolese route. It reaches 38.5 tons of carbon dioxide equivalent per ton of metal. This high intensity is driven by coal-fired power grids in Indonesian industrial parks. Geopolitically, Chinese entities hold an 85% equity stake in these Indonesian operations. This locks in long-term offtake agreements and limits Western access to non-aligned material. This dynamic mirrors the mid-20th century oil refining sector, where new crude grades forced a capital-intensive retooling of refineries. Today, Western efforts to build independent supply chains are blocked by Chinese equity and technology. The global agricultural economy is structurally dependent on mined potassium chloride. Unlike nitrogen, potash cannot be synthesized. A tight triopoly of Canada, Russia, and Belarus controls over 2/3 of global supply. In 2021, this triopoly produced over 30 million metric tons of potash. The imposition of Western sanctions in 2022 disrupted this rigid architecture. Belarusian output collapsed by over 60%, while Russian exports fell by more than 27%. This geopolitical shock removed over 7 million metric tons from the global market. Canada attempted to bridge the deficit by expanding production to 16 million metric tons. This pushed Canadian mines to 94% of active capacity, exposing the limits of Western supply elasticity. Canada's ability to stabilize the global market is constrained by physical geography. Potash must travel thousands of miles from Saskatchewan mines to Pacific ports. This journey relies on a rigid rail duopoly traversing narrow mountain passes. As detailed in the table, minor logistics disruptions trigger severe, nonlinear backlogs. The 13-day West Coast port strike of 2023 stranded over 8,000 railcars. This single event delayed 740,000 metric tons of potash and required 60 days to clear. The system operates with zero rolling stock redundancy. Every day of rail or port stoppage requires over 4 days of recovery time. This structural rigidity makes Western agricultural security highly vulnerable to localized labor disputes and weather anomalies. Potash demand is highly price inelastic because there are no chemical substitutes. When the global supply deficit peaked at 12.4% in 2022, spot prices surged by over 300%. Prices reached an unprecedented $1,050 per metric ton. The market exhibits extreme price-to-deficit elasticity. During the supply shock, each 1% reduction in global availability triggered a 26% price spike. This volatility immediately translated into higher fertilizer costs, threatening global crop yields. By early 2024, prices stabilized near $320 per metric ton. This correction occurred because Russia and Belarus bypassed Western sanctions. They established new overland rail corridors to China and redirected shipments through Baltic ports. This realignment mirrors the Great Grain Robbery of 1972. Once again, sudden shifts in agricultural commodity flows have exposed the vulnerability of physical infrastructure. The global food supply remains hostage to a highly concentrated and rigid logistics network.